In Part 5 of Lecture 4, we will discuss threads. Processes have at least one thread of control where it performs a sequence of instructions. All processes have their own address space, their own program counter, and their own set of resources. Threads are a lot like processes, except that they share the same address space and the same set of resources. The cost of switching from one thread in a process to another is not as high as switching between processes, and different threads within a process do not have the same level of protection from one another that different processes have. Threads allow traditional heavyweight processes to do more than one thing at a time within the context of, for example, word processing. One thread can read and process keystrokes, another can handle spell checking, and a third can coordinate the printing of documents in the background. It is easier to do these multiple tasks in the context of different threads of activity, as opposed to handling them as separate processes. File servers and web servers are very good applications for the use of threads, since they can easily share common data. Threads are a good mechanism for providing file service, because they can easily share data stored in cache memory. This could not be done as easily by heavyweight or separate processes, because they do not share the same memory. Web servers can easily use threads to share the same images that are being transmitted to different clients concurrently. Threads are a lot more responsive than processes. If a process is blocked while it waits for I/O to be completed, it cannot do the other tasks it needs to do. But if one thread of a process is blocked, the other threads can continue. By definition, threads share most of their resources, including memory and open files. This makes it easier for them to cooperate than it is for processes, and with less overhead. It takes much longer to create a new process than a new thread. In Solaris, it takes about 6 times longer. This makes it advantageous to create threads where possible, instead of additional processes. Lastly, since different threads of a process can run on different processors, it can make a process run much more quickly. Windows NT, Solaris, Mach, and OS/2 are examples of operating systems which implemented threads. Unix is an operating system which traditionally has supported one thread per process. Some systems support threads at the kernel level, and other systems have threads managed by user processes. In systems where threads are managed by the operating system, thread creation, scheduling, and management are all done by the kernel using its own memory space. This requires more work to be done by the operating system, and as a result, these threads have more overhead associated with them. Each of these threads are scheduled and managed directly by the kernel. User threads are an entirely different story. They are created, scheduled, and synchronized at the user level using the thread library, which is available to application programs. Because the operating system is not involved in their creation or scheduling, this is done very quickly. The problem is that the user must be directly involved in its management. If the kernel itself is single-threaded, a process can be blocked if any of its threads make a system call which blocks it. This requires the programmer to be more careful in handling multi-threaded applications. Some operating systems, such as Solaris 2, support both mechanisms. In Solaris, Kernel threads are separately scheduled by the kernel, and each are associated with a lightweight process, which can, in turn, have one or more user threads. The user threads are supported by a system library, but the kernel remains oblivious to the number of user threads associated with a process. User threads can have their binding changed from one lightweight process to another by the user thread library. Tasks, the equivalent of heavyweight processes, can contain more than one lightweight process, which can swap user threads as necessary.